discussed in that class. The page number was page number was 16. Equation number 112. So we talked about it last class, and this is just an example for that. So it's not thermodynamic, but you know that this remains constant through the process. So it doesn't matter how far the piston goes up or down, the temperature remains constant. Now I want to ask you before starting, in the real life, does that temperature remain constant? I know the mass remains constant, right? With a perfect accuracy. There are some molecules that always jump through the heat, but they're so tiny, you don't even see them. But what about temperature? It will decrease and increase. So if you go up, what happens? It's going to decrease. And if you rapidly go down, what happens? It's going to increase. But eventually, that increase in the temperature will transfer to the environment through the wall, right? And dissipate. So you're going to get the same, they come to the equilibrium with the environment temperature, with the atmosphere temperature, right? But we assume that the loading, so when I put the 10 kg here, I don't put the 10 kg and release it. So it rapidly goes down. Yeah, in that case, the temperature rapidly goes up. I assume that when I put the 10 kg, they call it quasi-static. I just release it very, very slowly. So the temperature almost remains the same, right? And the mass is the same. But the pressure will change. Pressure will increase, right? Okay, now the question here was, find how much of this delta H, delta height, the piston goes down when I add the 10 kg. And that was a meter Weber. Was it the final Weber or meter Weber? It was a meter Weber, right? So we said that, well, in order to find that, first let's see how much initial height I have, H0, right? When I don't have 10 kg, when I don't have loading, right? Let's see how much initial height I have. And then after I load 10 kg, what can I do? I can find the forces in all the mechanism, right? And also including the force on the piston. And then I can find the force that the fluid exerts on the piston, and then I can find the pressure by finding the force. And when I find the new pressure, what do? My temperature is same. You see, look at the equation. Your pressure is changing, so that this is new pressure. Your temperature is changing, is same, right? What other option do you have to change? The density. And the density is mass per volume. Mass is same, so what does it change? Volume. Volume, the cross section is same. This is a circular, cylindrical cross section with the radius, right? The volume is same. So what option do you have to change? The height. So that's the mechanism to get the new height, right? So what radius did I give you? Let me go to the photo I took of the white.
2 centimeters.
2 centimeters was the radius. I took a photo of whiteboard, so I don't miss it in class, because it's very important problem. Okay, now I want to first solve it again, find the initial H. I think we did it last time, but let's do it again. So what I'm going to do first, I find the, I have the density. Okay, let's start with that. P is equal to rho RT initially. So this is unloaded. There is no taking here. So the hook is free, right? So P is equal to rho RT. This equation is always valid. Now you have to check. If this is like water, this equation needs to be corrected. There is a Z correction factor, right? But for gas, for air, this is like a perfect equation. So assuming it's air is valid, next step, initially P is 100K, put here, 100, then to 3 kilopascal is equal to rho, initial density, or 0, I don't know, times the gas constant, 287, times the initial temperature, which is 28 converted to Kelvin, 273.1. Solve that for initial density, what do we get? Initial density is, yeah, 1.1 divided by 287 28 plus 273 and 1. So 1.157 split like that. kg 1.157 kg over meter cube. And now I know that the definition of density, let me write it here. Density was mass per volume. So I have the mass, I have the density, so the volume, which is basically the base volume times height, which is the initial height. So let's do that. The base cross-section area of this is pi times the radius 2 times -2 meter square times h0. So that's the volume is equal to the mass divided by density. The mass is 0.1 times 10 to -3 kilogram divided by density. Density was 1.157. Solve this equation for h0, what do we get? The initial height was 0.1 3 divided by 1.157 times 2 squared times pi. So the initial height h0 was 0.0688 or 6.88 centimeter. 6 centimeter and almost 9 millimeter, almost 7 centimeter. Right? So from initially, if I don't load it from here to here, h0 is 6.88 cm. Right? Now I want to load it. If I load it, how can I find the pressure here? Very easy. You remember vector statics, 5 steps. If you know your 5-step system, you choose your system, you draw your FEDs, you write your equation, you solve your equations, and then you verify your solution. Make sure you don't get negative pressure, right? Verification. Like negative friction, pressure. If you get negative friction in real life, you make $1 billion. So, step 1, system. Which one should I choose in my system? I want to find, that's the goal, to find the force exerted by fluid on the piston. So which one should I choose as my system? The piston, right? So this is my system. But maybe it's not enough, as I said before, vector static, this is an iterative procedure. So you choose something for the system, you draw your FED, you write your equation, and if equations are not enough, you do it again. You add extra system. Right? So this is my system. Let's call it system 1. And then you draw your FED. I'm going to draw it here. How do you draw a FED? You have to do surface force, body force. Right? So let's walk over the surface from the top. Is it touching anything, this piston? No. Then we come to the wall. To the wall is touching the wall, right? It's touching the cylinder. So that you're going to have a normal force. Do you have friction force, tangential force? I said frictionless. In the real life, yes, you do. But here, for assumption, frictionless. Why? Because you see you add the oil to the engine, right? So it has enough lubrication so that friction is almost zero. So don't write this friction force on FED. So you only have normal force. Call it F1. Continue working on the border. Then you call the interface between fluid and the solid, the structure. There is a force coming here, right, from the fluid. How can I model it? It's a distributed load. You agree? It's a distributed load. P0, this is the pressure. But it's not zero, it's a new pressure. Why? Because I added the 10 kg. So this goes down and compress that, so the pressure will increase. So let's call it P new. Or just simply call it P. But I know that P is not equal to P0. What is that? It's got to be greater than 100K, right? So let's call it P. And then you go continue walking. So this is not a force, this is the pressure. In order to get the force, you multiply that by cross-section area. You remember distributed load, you have to multiply the value of distributed load by the length to get the force. That's exactly the same. So do I have this? No, I don't have a new pressure. Do I have a normal force on the cylinder? On the cylinder to the piston? I don't have it. But who cares? We'll find it. Continue. There's going to be another force here, of friction. So let's call it F2. Continue. Walking, you come to the surface of cylinder, no touching, and then you come to this surface. There is a force on that coming from the link, right? Let's call it F3. Do I know that force? Yeah, we will find it. But do I right now do I know it? No. But I know the angle. The angle is
60.
60. You see, this was normal. Last time we discussed it, let's say assume that this is normal. So this is what? 60. So 60 with this angle, I do have the angle, but I do not have the force. Alright? So these are all the surface force on the body. For you remember vector statics, those people who have vector statics with me, they know it. The other one, what was the other component of FED? You have surface force and the other one, body force. Right? Do I have body force on the piston? The piston is still. Do I have weight? In the real life, we do. But in this case, you say, ignore it. It's very long. Right? So there is no body force. Otherwise, you put a W here, weight here. Right? So that's my FED for system 1. Now let's go to the next step. So I did system, I did FED, write equations. How many equations do I have there?
3.
It's a 2-dimensional problem. How many equations for a 2D problem? 3. Sum of force in x0, sum of force in y0, sum of moment 0. How many unknowns do I have?
4.
Yeah, 4. Can I solve it? No. So what should I do? Should I give up? That's what usually I do. Should I give up? No. Reiterate. So we came here, wrote the equation, we failed. Right? And then we reiterate here. We go choose more systems. So that's what I'm going to do. I'm going to choose another system here. Right? So let's call this system 2. So I'm going to write here. That's system 1. Sys 1. And then my sys 2 will be this. Once again, you do surface force, body force. I'm not going to repeat it again, so you walk over this border, you include all the external forces, and then you get this. There is no weight also. Do I have the force here? Do I have the force here on this end?
We have reinforced, but we don't know it.
Oh, yeah, we don't know it, but we already introduced F3, right? We already introduced, so do not define F4, because later you gotta say F4 is F3, they're the same animal, right? So I just put the opposite of this on this end. So that's a F3, only introduce F4. Now you may say that, if you are, I was expecting somebody to say that, but it's been a long time on vector statics, so I expect too much and forgot many of these things. But normally you expect that this is two component, F3x, F3y. We don't have the angle, right? If you add, like, if you have a link to a point and apply force, there got to be two components, x and y. There got to also be a moment, couple moment, but because it's friction, there is no couple moment. So you have x and y. Why I assume that there is 60 degree here?
36,
Because you remember two force members in vector statics? That if you have, let's say you put two components here, in fact, instead of that, I would have F3x, F3y. You can initially, the general case is like that, right? And F4x, F4y. And this is the most general case, assuming friction test. Most general case, you have also a couple moment if you have friction. But without friction, this is a general case. But look, if you rotate this component, so that you see this 90, you just rotate it 90 degrees just the way we did in vector statics. Again, it's the same thing. You have one component here, one component here. Do the same thing for that. So you have one component here, one component here. And if you write moment about this equation, what do you get? This becomes 0. And if you write moment equation, this becomes 0. So there is no way. The only possibility is this force should be along the axis. So we call this member two force members in vector statics. Just a review of what we did. So that's the reason I give you the angle. And I only have F3 this way. Right? Okay. So F3, what about the other option? Here, the other end, the same F3. I can make F4, but when I write sum of forces in this direction is 0, what do I get? F4 is equal to F3. So I just put F3. That's it. I'm done with that. So let me count the number of unknowns. This is already applied all the equations here. What are the equations? Sum of moment over this point. 0, that I got this tangential component gone. Sum of the moment about this point, I got the other tangential component gone. Two equations, and then sum of the force in x0, I got F4 is equal to F3. So how many equations I have total for two systems? Still 3. How many unknowns? 4. Gotta go back. Failed the second time. Gotta go back. Right? What do? Add one more system right here. So I'm gonna choose my third system. So that's my third system. Call it system 3. And then I'm here. I give system 3. And then I go to FTD, write equation, and hopefully I make a closure. You know, they call it closure. So here, the third system is this. So if I do FTD, should I put two components here? Should I do that?
No, it's a two force member.
Yeah, you see, I already have F3. You know, as an engineer, you want to make your life easy. In fact, if you're a quick problem solver, you don't even write this on a whiteboard. It's going to take you time. You know that the force along this link is constant, so you just need to from this system, you do that. Right? If you practice a lot. So I'm going to just put this F3, the reaction here, I'm going to just put it on the other side. There you go. But opposite on this system. And this one. And then for the FED, if I work, I get the reaction here, AX and Y. I have two reactions. So do I know AX? Do I know AI? No. And then when I walk over this border, I'm going to cut this cable right here. Right? I'm going to cut this cable. And do I have the force in the cable, T tension? No. But if I make one extra system, the T, the force in the table is what? 10 times 181. If you take these are the final system, summation of force in Y. So I'm not going to make that because it's going to take another 20 minutes. So the T here is just 10 times 981. So I'm going to put the tension here. There you go. T is equal to, coming from the last system, from the mass, 10 times 981. And the distance are given. I want to use another color. This is 1. This is 1 meter. This is 1 meter. That's it. That's my complete free body diagram for 3 system. And this system number 3. How many equations do I have for the entire thing, for all 3 systems? 9. But look, imagine we have already applied these 3 equations to get that. So 9 minus 3, how many equations do I have? 6. How many unknowns do I have? 6. 6 equations, 6 unknown. So I'm done. You see, I'm good. No more iteration. So next step, write the equations. Are we gonna write? Yeah.
Is there not a moment on A because it's frictionless?
Moment is 0 everywhere. Some moment 0 everywhere.
Okay.
But we use that information to get F3, right? Some moment about A, 0. Some moment is 0 about any point. It doesn't matter if you have friction or not friction. Some moment about 8.0, like one is positive, equilibrium, some positive. Okay? So what equation should I use first? I know I have 6 equations, and for 6 unknown. But which one should I write first? The way we do in vector static, because we have infinite time, it's not a vector static class. This is fluid mechanics class. But the way we do that, we populate all the equations here. So we spend about 15 minutes to write all the equations. And then we solve it. And then we verify. But right now, let's say we don't have time. Which equation should I use as the first equation to get into this system?
Moments ballet. Some of the moments ballet.
That's right. Some of the moments. I wish I could have said quiz with other people. Next time I'll say that, because this is hard. This was not easy. Some moment about A is equal to 0. So what do I get? No moment from this, no moment from this. I get 10 times 981. This force, I bring it down, right? So what's this moment on? 1 times cosine, thank you. 30 degrees. Positive or negative?
Negative.
Review of vector static, you guys.
Negative.
Yeah, negative. So 10 times 981 times 1 cosine 30 negative. Nothing from AX, nothing from AY. We're done with that. The last thing is this. What's the moment of that? F3 times? Thank you. Positive or negative? What else?
Sine 30.
No, this is already 90. You see, if this was here, I would move it. You remember in vector static? You had to break it down 3 steps. Move the component, get the moment arm, and contribute. Right? But this is right here. You see, this is already orthogonal to the moment arm. So you don't move it. It's just F3 times 2. Okay?
What he's saying is like the tension moment. You need the other component of it, right?
I'm sorry?
Because it's gone. It's,
Are you talking about the T?
yeah, don't you need the second?
Well, you remember T is already in the void, right?
Yeah.
So step 1, break it down. It's already in the void, don't break
Okay.
it. And step 2, move it. We brought it here. Now it's normal. You see that? So what's the moment arm? From here to here. 1 times cosine 30. You need to review vector static because next sections we are going to do we are going to do fluid statics, right? Like the water behind dam, things like that. And then there we do a lot of statics. And then we do Bernoulli equation, and I also always combine my problem with other systems, right? So you really need to go and review vector statics, and I don't say mechanics of material, but at least vector statics. What else? Do I have any additional sum of moments? You see, I'm completing this equation. Sum of moment, what A is 0. Is there any additional moment? No, I'm done with this, I'm done with that, I'm done with T, I'm done with F3. So the entire thing must be equal to 0. Look, one equation, one unknown. Solve for F3. What do we get for F3? F3 is equal to
42.48.
yeah, 10 times 981 divided by, so 42 F3 is equal to 42.4 newtons. Okay, I have F3, but look, the problem is asking for delta H, and the delta H requires a new pressure. So that means I'm trying to find the new pressure. Did I get the new pressure? This F3. So what should I do in order to get P? From this system, I go to the other system. This system is useless. We have already applied 3 equations, right? How many equations do I have here? Who said 4? Yeah, 3, right? And so here we have 3. But look, what equation is useful for me?
Sum of the forces on the Y.
Sum of the forces. Even you have to. Sum of the force in Y0. So what do I get? Sum of the force in Y0. Starting with F3. F3 sine 60. Positive or negative? Negative going down. And then, do I get any contribution from F2 and F1?
No.
No. And then I go to P. What should I do with P? P times?
P times the length.
A, the base.
There.
Yeah, the area of the base. Positive or negative? This is the force.
Positive.
P1A is force. Right? Positive. What else? Is equal to 0, nothing else. So the new pressure is what? If you saw that equation, the new pressure is this value, negative F3, I'm sorry, positive F3, sine 60, divided by the cross-section area. That's it. So let's substitute the number. I got my F3, it's right here. I got the cross-section area, right? All I need to do is substitute. So I get P F3, which is 42.48. That is in Newton, so it's right here times sine 60 divided by cross-section area, which is pi times the radius squared. Radius was 2 10 to negative 2 meter squared. All right? Go to your calculator, 42.48 sine 60 divided by pi times 282
Good.
squared.
2.93.
Yeah, 29.27 added. So this is added to the gauge. You remember we had gauge pressure. This is a gauge, but when they talk about gauge pressure, they're talking about the atmosphere pressure, ignore it. So you have extra on top of that. So when I wrote my FVD here, pay attention, when I wrote my FVD, I did not include the atmospheric pressure. I'm just including the extra pressure coming from the fluid, right? So this value, I get 42.48 Newton times sine 60 divided by pi, the radius squared, which gives me 29.27 kilo Pascal. Added to that. So what do I get for my new height? Just like I did for that. So I have my new pressure. Let's write the new pressure here. I'm going to write it. I'm not going to write it here. I'm going to write it here. So my new pressure is the atmospheric pressure, which is 100 kilopascal plus 29.27 kilopascal. So just like I did for the H calculation here, just reiterate, put it back here. So I have P is equal to rho RT. So I'm going to just put it here. Your new pressure is 129.27 times 3 is equal to your new density, rho times 287 times the temperature. Do I have new temperature?
No.
What assumption we made was static loading. That means we loaded very slowly. So the temperature is the same. So you just put, how much the temperature was?
301 Kelvin.
Plus 27.1. So solve that for density. So we come with a new number. I'm going to just write it there. That's the reason I didn't write it there. 129.27 E3 divided by 287 and 28 plus 17. So you get new density is equal to 1.6. Sorry, 0.163 kg per meter cube. Right. So you get. Are we doing something wrong here?
I got 1 point.
Yeah.
I got 1.5 for my number.
You put 129.27 times 10 to the third, but over here you put 29.27 times 10 to the third.
Hold on.
For the pressure.
For the pressure, I put 129.27 E3 divided by 287 times 28 plus, okay. I put 2007 for temperature.
That'll do it.
I'm sorry. So you get 273.1, okay? So you get 1.49. Can you please double check my result with your calculator? Because sometimes I mix it like some decimal point, and then that makes a huge difference in the one computer. So you get 1.49, and there is a 5.6 kg over meter cube. So that was rho 0, and this is new density, right? So by the same iteration, we do H nu. So I wish I could write it here. So put here, this was H0. So instead of this density here, now everything remains same except, you see this is, let's write it here. The density is equal to mass per volume. So this equation is that. So I put the volume here, you see, But this is the H nu. Let me write it here. Instead of explaining it, I can just simply write it. So from that equation, I can bring V here and bring density here. And for V, I can write pi 2 10 to negative 2, just like that. There is a square here. Area times mu H is not H0, it's mu H is equal to mass. Do I have leakage in the cylinder? No leakage. So mass is same. So mass is just the same, 0.1 gram 10 to negative 3 kilogram divided by the final density, which is basically this guy, 1.496. Right? So divided, so you get 0.1 negative 3 divided by 1.496 times 5 times 2 negative 2 squared. So you get 53 like that, 0.0532 meter or 5.3 centimeter. Right, look at it. I want you to think about it. From here to here, your H nu is what? Your H or H nu is smaller, 5.3 centimeter. Initially, it was initially it was 6.9. H0 was 6.9. Now it's 5.3. How much delta H you came on?
1.6.
4 point?
1.6 or
4.6. What number did you have on whiteboard?
I kind of forgot what number I had yesterday in my calculator this day right now.
Okay. You had something like a 4. But it was not 4.
So delta H is H0 minus H1.
Yeah, so basically the changing is, forget about thickness of piston, the center line. The change between that is what? Delta H, right? Which is 6.9 minus 5.2. So this is a fluid mechanical problem combined with the structure, but all you needed to do was P is equal to ORT. We haven't given you any new equations since vector stack. The only new equation is that equation of state. Soon we are going to throw a lot of equation at you called Navier-Stokes equation, and you're going to solve a lot of different concepts. Now let's go to the shear stress, page number 18, and discuss it. Okay, we talked about shear stress, and shear stress shear stress was the motivation to define fluid. Now, that was the motivation to define a fluid. And we said that fluid is something that cannot resist its own developed shear stress field. Right? Now, the question here is, how can you come up with the shear stress in fluids? Right? Let's say you have this is your surface, and you got some fluid here, and what you do, you put a flat plate on it. This like plate, flat plate, and you push it down so you come in contact with fluid. So between that is just fluid everywhere. And what you do, you drag this plate to the right. all right, with some velocity, v. And this wall is constant, so the velocity of wall is 0. This is wall, right? So what happens here? Well, as you can see, the particle close to this, fluid particle close to that plate will stick with the plate. So let's say we have a very powerful microscope that we can zoom infinite time near the wall. What do I see for the particle of fluid just near the wall? They stick to the plate. So what's the velocity of them?
Same velocity.
The same velocity. So they're gonna go with higher velocity, right? With higher velocity. What about particle? If I bring my microscope here and zoom here, what do I get for velocity of fluid particle near the wall here? 0. So as you can see, the velocity from 0 here goes something to a higher velocity like v. So here velocity is v, here velocity is 0 for fluid, right? For the fluid particle. And you know that these particles, they do not have the same velocity. Why? Because velocity is 0 here, velocity is v here. So there should be some variation. And we don't know. We don't know how it works. So how can I know it? Well, the first person, he went to the lab and he did this setup and he observed. So he put some dye in the fluid, he observed how those particles are moving with the plate. And the interesting thing happens here, if you put just regular water or air, right? So if you have air or regular water, this distribution is a perfect line. It's like a perfect, really, really perfect line. Just like that. But if you put something a little bit more creepy, like honey or ketchup, this distribution is not linear, is parabolic, or maybe here. So the velocity, yeah, it goes to v, and it's 0, yes, but this variation is not linear. And I'm going to tell you, this type of fluid that is linear, they call it Newtonian. Newtonian fluid. It's just the property, the nature of those molecules, the way they bond together, that did make this profile to be like. They call it Newtonian fluids. And all the fluids we saw in this class is what? Newtonian fluids. Right? These fluids that they do not exhibit a linear relation, they call non-Newtonian fluids. So this is Newtonian, these are, including these two, non-Newtonian fluids. And it used to be a very sophisticated field before the invention of computer. Why? Because you see, for Newtonian fluid, what's the relation between velocity and height? It's a linear. If these are very extremely close, if you have a larger gap, you get something boundary layer. We will talk about that later in this semester. But if they are extremely close, right, this relation is line. And in that case, you can write the relation between shear stress and velocity. You can say shear stress is proportional to the gradient, the slope of that velocity. du dy. du dy. Let's say this is your y-axis, right? Y-axis, and this is your velocity. So u, let's call it u function of y. So uy at this distance h is v. Uy as y0 is equal to 0. So the derivative of u with respect to y is proportional to shear, only Newtonian fluids. And then if you want to convert that to the equation, we get tau is equal to mu, the constant of proportion, du dy. That's it. This is the relation we find for shear stress in Newtonian fluid. and you use that relation to solve a lot of problems. Flow in the pipe, flow in the open sections, and it makes your mathematical solution of problem very easy because it's a linear relation. So you can do have you solved ordinary differential equation? Did you have ordinary differential equation? That's what we end up this semester. If you substitute this into Navier-Stokes equation, all you need to do is solve ODE, like double integration, things like that. But for non-Newtonian fluid, like this or this, then you have things like this. Tau becomes like mu1 du dy squared plus mu2 square root of du dy plus mu3 du dy to the third power. Very complicated relation. So you have nonlinear, as you can see, the third power, the second power, the square root of the velocity. Now, this used to be a very complicated field 50, 60 years ago, before the invention of computers. Why? Because they used to use analytical technique to solve the these equations are. It makes the it makes the differential equation very hard to solve. If you have the differential equation, you already know it. When they say nonlinear differential equation, you cannot solve it analytically, right? Sometimes you can't even solve it. It doesn't matter how bright you are. You can't solve it. There is no way to solve it. So this field, non-Newtonian fluid was like a big one 50 years ago. But after the invention of computers and all this numerical solution problem, they used technique to linearize this into a basic linear problem on a small tiny elements. They can simulate this fluid and they can come up with very accurate results. Now next class I'm going to show you some simulations. Like you have a plastic or pseudo-plastic fluid, you pour it on the surface and you completely compute. I'm going to show you some simulation and then we continue.